Right. So last time we discussed what are the logic circuit inside the CPU, and under this we are going to discuss couple of circuits. And the first thing that we have discussed is half adder, right? Now, what do you mean by half adder? You will have two inputs, and then you will have two outputs as sum and carry. This is to represent single bit additions. When you say single bit additions, we know that we have four possibilities. When you add 0 and 0, we will get 0, 0, 1, we will get 1, 1, 0, 1, 1, 1 is, we have 1, 0. So the summation would be the last digit. That means it will be 0, 1, 1, 0. And carry will be 0, 0, 0, 1. So now when you want to identify the expressions for this, we can look at, sum of product terms. So sum expression, we will get A bar B plus AB bar. That is, we will already know from the theory that this is exclusively O. So A plus B. And then carry expression, we have only one, and that is A dot B. And the circuit we can represent like this, right? So that is for the half adder. And then we were discussing the full adder. Now, what do you mean by full adder? When you have three input. Now, usually what happens when you are adding bits, we will have at least two numbers. And then sometimes we will get a carry in, we call it, from the previous, right? The value will carry it forward, and that will be right. Then let's look at the simplifying this one. So first of all, I told you we need to know in both ways. That means you should be able to simplify this using Boolean expression or Boolean algebra. At the same time, you should be able to, use Karnaugh maps. So we were discussing that part, right? So under that now, we discuss full adder, and we have already written the sum expression. So now we need to, write down carry out expression. Just for the carry out, we can say we need to write the carry out here. So carry out will also be like this. So let's write down the expression for carry out. So I will take a text here. Right. Now the carry out should be, now we have to write the expression from here. Now we know that if you use it as a sum of products, we will have A bar B C in. We have A bar B C in plus then A B bar C in plus A B C in dash plus the last one A B C in, right? again, we have 4 statements. Right. Now, if I take the very same, that means if I draw the Karnaugh maps, so let's draw the Karnaugh map here. Right. So in the Karnaugh maps, then we can write down what are the values. So we will have, this is, let me start from the beginning. Let me delete these values. Yeah. So now I have to fill these, right? You don't have to wait until I do, you can do it. Yeah, okay. So when we have the first one, that is A bar, then we have BC, that is this one is 1. And then we have A, B bar C, this one. Then A, B, C bar, B, C bar, this is the one, and A, B, C. Right? All the others will be 0. Yes. Can you simplify and tell me what is the expression now we are getting? Right. So let's simplify using Karnaugh maps. So in this case, there's no group of 4 bits. So we have to rely on group of 2 bits. So if I start from here, I can combine these two together, right? And then to cover up this one, I can combine this one together. And then to cover up this one, so I will have this. Right, maybe I'll use different colors. Right, for this one, what will happen? We will get BC. So this is BC. And then yeah. So let me cover this one. So this one, we know we have A and B. So this will be AB. Right. And then let's take another color. Right. So I'm going to combine these two together. Yeah. And this is AC. Right. For the simplification, now we can say it's Yes, AB plus BC plus AC, right? Okay, right, that's the answer. Can you draw the circuit now? Yes, draw the circuit. So we can say if the C out equals AB plus BC plus AC. Now this is using Karnaugh maps. Now similarly, I could have, use Boolean algebra to simplify this. So in that particular case, we can take this one. Let me show you how we could do this. Yeah. Right. So if I going to do this, what will happen? I'll have to take two terms at a time. So I will take this one ABC in with each term. So I'm going to take this term with all the others. So simply that is what exactly we did in Karnaugh maps also. So I'm going to use A bar B C in plus A B C in, and then we'll take the second term A B bar C in plus A B C in plus A B C in bar plus A B C in. Right. Now that we have copied, now we can simplify each of the two terms. So the first one, we will have BC in, then within the brackets, we will get A bar plus A plus, then the next two terms, we have A C in, and we will get B bar plus B, then plus we have AB, and within that we have C in dash plus C in. Right. So we will have BC in plus AC in plus AB. AB, BC, AC anyways. Right. This is how it looked like. Now, this is same as the way that we have did earlier. Now I want you to draw the circuit. Right? Simplify. We have to have three inputs in this one. We have to have three inputs, right? And then for the sum, we will have XOR gate with three inputs. Then we have three AND gates and one OR gate. Yes, can you draw this? So let's draw the circuit. And you can do before me, and we can say full adder circuit. So in full adder circuit, we have to have three inputs. To draw the circuit, we need like one exclusively OR gate, and then three AND gates and one OR gate. So the inputs are A, B, C. So we have to have A, B, C are the inputs. Let's say these are the A, B, C. We'll have B, C, right? So let's see, we have A, B, C. So those are the inputs, right? Now let's connect the three. So the first one is we have A, B, C for exclusively OR gate. So let's connect A here. Right, I connect A. Then we have to have B. And then we have to have C. That is a mistake. Right. So now we know that this is what we expect, and this is the sum. We can say this is the sum, right? Okay. Now we have to combine AB. So in this one, I will have AB. I'm going to connect AB. Then we will have BC. B, and then we have C. And then we have to have AC. A, and then we have to have C. Right. Now almost done. We'll do the final connections. We can connect A and then we have B and then we have C. Right. Now we are supposed to connect. So the last one we have to connect now here. We need to connect C. And with that one, actually, we have finished. And these are the connection. I'll put some small dots to indicate that the connections. The first one we have AV, then we have BC. Okay, so B we don't have put. There's no G. Okay, we have BC and we have AC. Right, now that we need to connect the two. Right, and finally, we can say C out, okay? So we can have, okay? So here is the final one, the circuit for the full adder. Okay, right. So in this part, we will look at how we can store bits in digital circuits. Right? Now, what do you mean by storing bits? And for that, we are going to talk about what we call feedback loop. Right? So when you say feedback, means we are getting output as one of the inputs or feedback circuits, or we call feedback loops. So to do this, let's start with the simple circuit. Let's say we have, right, we have a circuit, right? And let's assume we have some inputs and outputs. So I will have some inputs, and then I will also have some outputs, right? So what you see here is some inputs. So this is input, we can say, right? And then this is output. Right. Now, usually what we have discussed so far is circuit like this. You have a input and you will also have some output. But when it comes to storing bits, the first thing that we are going to look at is feedback circuits. The idea of feedback circuit means the output we are going to connect to the input, right? The output we are going to connect to the input. Now, when I say output which connect to the input, what that means? So you get the output here. So that would be another input, right? So that means we will take one of this and put it as another input. Right now, let's say we have a second input, but remember this second input comes from here, right? So you will take from here, right? And then it will connect as the input. So that's what will happen in a feedback circuit. And we will see the very same idea we will use to build, to store values. So output is again connected as input, right? Output is a connected as input. Let's write down output the underlying. So sequential circuit means, now we talk about we have inputs and outputs similar, right? Similarly, we will have inputs and we will have outputs some of the inputs are coming as the input from the output, but actually it comes from the next state. What do you mean by this is the previous state is actually input here. And what you get from here is the next state. So actually there will be some memory, which means we can store bits. That's exactly what we need to discuss. Right? Can you draw this one as well? So let's write down what sequential circuits are, because we wanted to look at. Let's write down. We can say in sequential circuits, the output is depend on not only the input, not only the, we can say present input. I will explain why we say present input. Present input. And but also on the previous inputs and outputs. Right? So the output is not depend on the present input. So these are present and also previous, but previous state we will get it from here, right? So that's what we are going to do. Right. Now let's look at some example circuits for this. And when you look at circuits, the flip-flops are what we are going to discuss under this, right? So flip-flops, let's have a subtopic, flip-flops. Right. So under the flip-flop, let's take down a flip-flop can store one bit of information. So flip-flop is a circuit that we can use, right, to store one bit of information. In sequential circuits, in sequential circuits, in sequential circuit, flip-flops are the basic storage elements. So we need to discuss what these flip-flops are then, right? So there are several flip-flops. So there are four basics. There are four basic flip-flops. SR, JK, I will explain those. D and T. In the exam, you don't need to know everything. But we want to know that, okay, there are several flip-flops we can use. So let's start with the basic flip-flop, right? So let's start with SR. So SR means set reset. So let's start with set reset. We call SR flip. Right, I will explain now. Right, now that we have discussed set reset, what we have here is two NAND gates could be used, right? Two NAND gates could be used, right? So first of all, let me draw the circuit. So let me have two NOR gates. I'm going to get two NOR gates. And this is how we are going to connect this one, right? So just have a look at it. So we are going to combine, right? So when you want to combine, what we are going to do, right? We are going to define set reset like this. For example, set will be here. I will start from here. So set, let me say this is S, right? And reset will be here. Right? So we have reset. So that is reset. And then this is set. So these are the inputs, right? Right. Now output, it's very interesting, comes from the output is going to connect to the this input, this output is going to connect to the this, right? So that's what we are going to do, right? But before that, let me extend this. So these circuits are defined in a way that, okay, so we have two outputs here, right? And we'll connect the inputs to here, right? So that we are going to connect these outputs to the inputs. So that's what we are going to do. So we'll take these outputs, right? So I'm going to take this output. Here also we have output, right? And then we have inputs. So what will happen here, I'm going to connect these two together. So input from this, right? We are going to connect here. Right? We are going to connect these two together. Similarly, right? Here also input output is going to connect to the input. Right? So the output is, this is Q, right? And if this is Q, the next one will be Q bar, the complement of Q. So this is interesting, Q bar, or you can say Q dash. My case, I'm putting like this, but you can use bar, right? So the output is here, the Q, and this is Q bar. Okay. Now, before we move on, I would like to, look at what is the output of NOR gate that we need to know, right? So let's remember what NOR gate means. So we know in NOR gates, if you have A and B as the input, we'll have A plus B bar, isn't it? We have A plus B bar. And what we know, let's say this is Q. If you have A input, B input, and Q output, it goes like 0, 0, 0, 1, 1, 0, 1, 1. Addition will be 0, but bar will be 1. Addition will be 1, bar will be 0. Addition will be 1, bar will be 0. Addition will be 1, bar will be 0. This is what you need to know how to design the circuit. Now that we have drawn the circuit, now we can write down the truth table for this circuit, right? So let me start. Now, when you have SR flip-flop, right? Let's start. I'm going to look at SR, right? Let's write down the values. Now, when you write or draw truth table for this, we have to be careful about this because the output is also connected to the input. So when you talk about S and R, right? So you might think we have S and R, right, as the input. No, not only S and R, you are getting some input from the previous state, isn't it? So that means you have to get that one also into consideration. So now to denote that, I will say this Q as time of t, we will say Qt. Why we said Qt here? It's very important to understand, right, what will happen in the next state. So this is previous state. And then I can say, okay, so we have these inputs and the outputs after the t. So I'm going to say this is Qt plus 1. The reason is now we have a time previous input. So previous output we have taken as input, previous output. Previous output, if the current output is t plus 1, we know previous one is Qt. So that is actually a simple representation to understand what is happening. And let me put Q bar t plus 1 as well. Right. Now there could be several inputs. So what are the inputs? We know we can have 0, 0, 0, and then we have 0, 0, 1. We have 0, we have 1, 0, then we have 0, we have 1, 1, right? So you can continue this. Then we have 1, 0, 0, right? I will copy paste. And I will make these are ones. We have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. Okay. Now, let's look at how this circuit works. So in the exam, you don't have to remember everything, but let me say how we are going to do this. So that what it means, let's carefully look at how this will work, right? So first of all, you have to look at S and R. We know that S is, now let me put values. So initially we have 0, 0. So S is 0. R is 0, right? And then we say Q is 0, previous Q. That means this one is 0. So what is Q bar then? Kanta? If Qt is 0, what is Q bar T? The value here. It should be 1, right? Okay, now that's why now you can see, now we know everything. Now what is the output? Can you tell me what is the output now? What is new Q plus 1? If you have 0, 1, what is the output? And if you have 0 and 1, what is the output for Q?
0.
You can look at the table. If you have a 0 and 1, right? It will be 0, right? So that means this is 0. Mavinia, if you have 0, 0, what is the output? You can type in the chat. If you have 0, 0, the output is 1, isn't it? Now you have to check, this should be match. Now output is same as the input. This one is also input. So we can write down, okay, Q is 0, Q bar is 1. No issue. First one. Okay. Got the point? Are you comfortable now? Right. Now let's look at the next states, right? So what do you mean by next states? Right? What do you have? The next one we have SC 0, R is 1. So SC is 0, R is 1. So we need to change this. And Q will be 0. So these ones will be same. So output we have to define. But what we know is R is 1. Right, Kanta. What is Q this time?
Zero.
It's 0 because the inputs are 1 and 1. So Q will be 0, no issue. It will be matched here. Then Mavinia, if the input is 0, 0. Yes, this will be 1. So again, match with the input. So there's no issue. We can say, okay, Q is again 0. Q bar will be 1. Okay, now we have done 2. Next one. Now to look at the next one, we can remove the inputs. What we need is to have Q is 0, so no change. And this time, SC is 1, R is 0. We have to say SC is 1, R is 0. Mavinia, what is the output Q here when you have 0 and 1? Yes, SC is 1, R is 0. And Q is 0, so Q bar is 1. So Mavinia, when you have 0 and 1, what is the output? Yes, when you have 0 and 1, the Q is 0. Kanta, when you have 0 and 1, what is the output?
0.
Okay, so this is 0. Now, when you have 0, there's a problem, right? Because this is not matching. So what happens, since this is unstable, so this 0 will affect here. So that means this is becomes 0. Now what if? When you have 0, 0, what is the outcome? Yes. See what have happened? Now, when you have output 0, now this is not matched, which means this is unstable. That means you can't, in the same line, you can't have two different values. So this will affect, meaning like this also changes to 0. Now the inputs are 0, 0. My question, Kanta, what is the output now?
1.
It should be 1, right? So now this should be changed to 1. Now when this puts 1, again, there's a mismatch. So because of the mismatch, this will also forwarded, which means now this becomes 1. Right? Now when you have 1 and 1, what is the output?
0.
It's 0. Now it's, you can see, it's matched. No changes. So the final outcome is this time Q is 1, Q dash is 0. Is it clear? එතන වෙච්ච දේ තේරුණාද? ඒ කියන්නේ output එකයි input එකයි වෙනස් වෙන්න බෑ. එකම circuit එක. එහෙම වුණොත් මේක තව පාරක් වැඩ කරනවා unstable හින්දා circuit එක settle වෙනකම් මේක යන්න ඕන. So now what has happened, right? It will go through a couple of times, now settle. So after this point, there's no change of the circuit. Right. Shall we start the next one then? So the next one, right, now we have to change the values. Q should be 0, so that means output we have to remove anyways. And this also we need to change. And we have R and S both should be 1. So the both should be 1. So R is 1, S is 1. So Q is 0. So that means this is 0. So Q bar, that should be 1. Okay, Movinia, what is the outcome of the first time when you have R1 and Q1? We have 1 and 1. The output is, yes, we have 1 and 1, isn't it? So the output is 0. So that is matched, no problem. So when you have 0 and 1, what happens? Kanta? So this will be 0. When this is 0, this is not matched. So we have to make it, this is 0. Now what have 1 and 0, right? So 0 and 1, we have 0. So this is not matched. We have 0. 1 and 0, we will have 0. Right. Now there's an issue. Can you let me know what is the issue? Looks this is okay, but it's not okay. Why? I make a galloping make it. I මං කිව්වා මේක output එක Q නම් අනික එක Q bar දෙකම සමාන වෙන්න පුළුවන්ද? නේ? Q0 වෙලා Q bar 0 වෙන්න පුළුවන්. No, you can't. There's an issue. So we have to avoid this. We normally call avoid this state. This is bad because we have to have Q and Q bar. Right. Let's move to the next one. We have 1, 0, 0. So we are going to update again. Right. So Q is 1. So this is 1. Right. S and R is also 0. So we have 1 here. This is 0. This is 0. Now when you have 0 and 0, we know this is 1. It's matched. When you have 1, 0, this is 0. It's matched. No changes. So Q will be 1. Q dash will be 0. Next one. Q is 1. Then S is 0. R is 1. So we have to change this one. Right, this is 1. R is 1. So when you have 1, 0, we know this is 0. Right? So that means this is not stable. This becomes 0. Right? So when you have 0, 0, this is 1. Again, not matched. So this will be 1. So when you say 1, 1, this is 0. That is matched. 0, 0, this is 1. It's matched. So which means the next one, Q is 0 and Q bar is 1. The next one, we have 1, 1, 0. When you have 1, 1, 0, so that Q is 1. Q is 1. S is 1 and R is 0. So we have to change everything. So now let me put Q is 1. So that means this is 1. That means this is 0. Right? S is 1. R is 0. Right. Kanta, can you give me what is the final output according to this one?
Q1, Q bar 0.
Yes, what is Q?
1.
Yes, it's 1 and Q bar is 0, right? So when you have 0, 0, this is 1. And then when you have 1, 1, this is 0. It's matched. So this is 1, this is 0. Right. Next one. We have to have all ones. So I'm going to erase this one and these two. Right. So we have 1 and 1. And Q is 1, then this is 0. So what happens here now when you have 1, 0, we know this is 0. It's not matched. So this becomes 0. When you have 1, 0, this is 0. So that is matched. The problem is again, this is 0 and 0. It can't be because the way we have defined, the output should be Q and Q bar. So this state is also we have to avoid. Right? This state also we need to avoid. We normally say you need to avoid here. Right. Let's take down this one and we'll summarize. So let's summarize this one. Now, to summarize what is R and what happens here, right? We can consider only three parts, because in the circuit, what is important here is S, right? What is important here in S, R, and Q, output, that is T plus 1. This is only what you need to remember about this. Right now, when you have two inputs, we know we have four states. Now, can you tell me what is when you have the input 0, 0? Right? Look at only 0, zeros and tell me what is output. When SR is 0, 0, you look at here, 0, 0, right? Q is 0. When we have 0, 0, Q is 1. What is it when you have 0, 0? Yes? Any ideas? So look at this. When you have 0, 0, the previous state is 0. When you have 0, 0, previous state 1. So can I say that when you have 0, 0, it will give me the previous state? Can I put like this? හරිද පුතේ? තේරුණාද කිව්වේ? ඒ කියන්නේ කි අදහස පුතාලට පේනවා දෙකම S උයි R උයි දෙකම 0 නම් we know the output is the previous state. So when you have 0, 1, what is the outcome? Yes, when you have 0, 1, look at when you have 0, 1. When you have 0, 1, outcome is 0, 0, 1, outcome is 0. So we can say, okay, this is 0. We normally call this as set. This is set. Right? And the next one is when you say 1, 0, you can say outcome is 1. And this is what we call reset. And when you have 1 and 1, we need to avoid. I will put a cross here. Right? We are not going to consider this state. Right? And that's how the working of SR flip-flop. So you right? It looks like this. Okay, with that one, we can conclude our unit number 4, logic gates. And we'll start examination questions.